already know from experience that blowing air into a balloon increases its volume. You may also have noticed that raising the temperature of a balloon causes it to expand in volume, or that placing the balloon in an environment with a lower pressure will also cause it to expand. And, of course, you know that if the temperature of the balloon is increased past the point where it can no longer expand, it pops. All of these phenomena are the result of the behavior of the gas in the balloon. Investigation into the behavior of so-called ideal gases from both experimental and theoretical perspectives is the topic of this section. All gases exhibit similar physical behaviors when at very low densities. We call such gases ideal gases. The variables that determine the behavior of an ideal gas are its mass, pressure, volume, and temperature. Beginning in the late 17th century, scientists began to set forth what we now collectively refer to as gas laws, and all described relations involving these variables. These experimentally determined laws provide quantitative explanations for the behavior of ideal gases. The English chemist Robert Boyle observed that, when held at constant temperature, the volume of a gas is inversely proportional to the pressure applied to it. This relation is now known as Boyle's law, and it explains why a balloon expands when placed in an environment of reduced pressure. The gas volume increases with decreasing pressure. We can predict the change in volume of a gas resulting from a change in its pressure because, according to Boyle's law, the product of the initial pressure of a gas and its initial volume is equal to the product of its final pressure and final volume. If a given quantity of gas at constant temperature has its pressure reduced by 1/4, how will this affect its volume? Correct. Its volume will increase by a factor of 4. Nearly a century after Boyle's discovery, the French scientist Jacques Charles determined that when an ideal gas is held at constant pressure, the ratio of its volume to its temperature is a constant. Charles's law, as it is known, explains why a balloon expands when its temperature is raised. The gas volume increases with increasing temperature. A plot of volume versus temperature of an ideal gas at constant pressure is essentially a straight line extending down to the point at which the gas liquefies. If this line is extrapolated to a theoretical zero volume, the corresponding temperature is known as the absolute zero of temperature. It is this absolute zero that forms the basis of the Kelvin temperature scale and corresponds to negative 273.15 degrees Celsius. Kelvin temperature units are always used in calculations involving ideal gases that deal with absolute temperatures. We can now predict the change in volume of a gas resulting from a change in its absolute temperature because we know from Charles's law that the ratio of its initial volume to its initial temperature is equal to the ratio of its final volume to its final temperature. If the temperature of a given quantity of gas at constant pressure is increased by a factor of 2, what will be the effect on its volume? Correct. Its volume will increase by a factor of 2. Another Frenchman, Joseph Gay-Lussac, determined that at constant volume, the pressure of a gas is directly proportional to the absolute temperature. Gay-Lussac's law explains why a balloon pops. When the balloon structure can no longer expand with the gas, the volume is constrained to remain constant. The gas pressure then increases with increasing temperature. The increasing pressure eventually causes the balloon structure to fail catastrophically. The three gas laws can be combined into a single statement that for a given quantity of gas, the product of its pressure and volume is proportional to its temperature. So far, we have not determined how the amount of gas present affects the other quantities. Experimental evidence shows that, for constant temperature and pressure, the volume of a gas increases in direct proportion to the mass of the gas. This explains why a balloon expands when air is blown into it. The volume of the gas increases as the mass of the gas in the balloon increases. It turns out that the number of moles of gas is a convenient measure of the quantity of a gas. Remember, 1 mole of a substance has a mass equal to the molecular mass of that substance. By using moles in our calculations, the quantity of gas is independent of specific gas being considered. Now, with the addition of a universal gas constant, our proportion becomes the ideal gas law. We can use the ideal gas law to calculate the volume of 1 mole of gas at standard temperature and pressure, or 273 kelvins and 1 atmosphere. By rearranging the equation to solve for volume, we see that the volume of 1 mole of gas is about 22.4 liters. This is a useful quantity to remember, as it is the same for all ideal gases, and knowing it can make some calculations simpler. For example, if you want to determine the mass of oxygen gas in a 500-liter container at standard pressure and temperature, you need only divide 500 by 22.4 and multiply by the molecular weight of oxygen to arrive at the answer. The number of moles of gas is equal to the number of gas molecules divided by Avogadro's number. We can simplify matters by defining a new constant known as Boltzmann's constant, which is equal to the universal gas constant divided by Avogadro's number. The ideal gas law can now be rewritten in terms of the number of gas molecules. The owner's manual that comes with every car states the proper pressure for the car's tires. This figure is a cold pressure, and thus should be measured before driving the car. Why? Because after you drive the car a while, the temperature of the tires increases and therefore, according to the gas laws we have studied, the pressure of the tires also increases because the volume remains relatively constant. Although we can explain the relationships involving the pressure and temperature of an ideal gas on a macroscopic level by using our gas laws, we have not yet fully described what is happening in gases on a molecular level. How can the properties of pressure and temperature be described in terms of the molecular properties of a gas? A concept known as kinetic theory does an admirable job of describing these characteristics. The basic premise of kinetic theory is that matter is made up of atoms and molecules that are in constant random motion. In formulating kinetic theory for ideal gases, we must make certain assumptions regarding the molecules making up the gas. The first is that gas is made up of many randomly moving molecules. Gas molecules are usually very far apart from one another, relative to their size. We assume that gas molecules interact only by collisions, and that these collisions obey the laws of Newtonian mechanics. Finally, kinetic theory assumes that collisions between molecules, or between a molecule and the wall of a container, are elastic. The pressure a gas exerts on the walls of a container is the result of molecules colliding with the walls. If we assume collisions with the wall are elastic, each molecule of mass, m, exerts a force on the wall with a magnitude equal to the time rate of change of the molecule's x component of momentum. After bouncing off the wall of the container, a molecule may again collide with the container. The time interval between the collisions with one wall is related to the x component of the molecule's speed and the distance between the walls. We can thus write the force on one wall in terms of the square of the molecule's x component of velocity and the distance between the opposite walls. The random motion of many molecules is needed to produce a relatively constant force on the container wall. Therefore, the net force is related to the total number of molecules and the average value of the square of the x component of the velocity of those molecules. Because the velocities of the gas molecules are assumed to be random, the average value of the square of the velocity of the gas molecules can be related to that for the square of the x component of the velocity. Remember that pressure is equal to the force per unit area. Thus, since the volume of our container is its length times the area of its face, we can derive an equation for the pressure of the gas in terms of its molecular properties. Our derivation is valid even though we ignored collisions between molecules. Statistically, such collisions average out, and therefore they do not affect the number of collisions with the container walls. Our result is also independent of the shape of the container. Now, by multiplying both sides of our pressure equation by volume and combining the result with the ideal gas law, we can relate the temperature of the gas to its molecular properties. You can see that the average kinetic energy of the gas molecules is directly proportional to the absolute temperature. This relationship can also be applied to liquids and solids, thereby providing us with a quantitative explanation of why molecules making up a substance move faster when the temperature of that substance increases. We can calculate how fast, on average, molecules are moving by taking the square root of the average of the square of the molecular speed. This is known as the root mean square speed of the molecule. Let's calculate the root mean square speed of a helium atom in a balloon at a room temperature of 293 kelvins. First, we calculate the mass of one molecule of helium gas by dividing its atomic mass by Avogadro's number. Plugging this into our equation, we see that the root mean square speed of the helium atom is a very fast 1,350 kilometers per second.